Hello everyone. The title of the paper I'm going to talk about is called Underwater Sound Propagation for Virtual Environments. This is the outline of our report. Both visual and acoustic rendering are of importance for building three-dimensional environments in VR. Sound propagation can provide one with spatial information such as directions and distance for virtual underwater training simulation. Sound plays a critical role which is important for real-time target location and enhancing the immersiveness of the simulation. In underwater games, realistic and fast sound feedback is also required for immersive user experience. This paper possesses a novel method tailored for simulation of sound propagation in non-uniform underwater environment. We combine the popular normal mode method in physics with an improved ray tracing method for sound propagation. The main contributions can be summarized as follows. We propose a novel framework specific to interactive sound propagation simulation for underwater scenes. By combining the normal mode method in physics and ray tracing method in computer graphics, our method can achieve vivid underwater sound propagation effects in an efficient manner. Through setting appropriate threshold to switch ray tracing methods and choosing reasonable interpolation and extrapolation points based on local scene information of the listener at runtime, our method allows sound rendering with moving source at interactive rates that has great potential for applications in VR. Current sound propagation simulation techniques can be grouped into three categories. There are numerical acoustic techniques, geometrical acoustic techniques, and hybrid techniques. Next, we introduce our method. The input includes scene information and audio signal. At the pre-processing stage, the calculation space is divided into boundary scattering region, object scattering region, and medium scattering region. The sound field is then evaluated by the proposed hybrid method. At runtime, the pre-computation results are traversed and the IR is obtained by interpolation verification at positions of the moving listener. The division of space and frequency domain is dynamically controlled according to the size and the position of objects in the scene. Frequency domain decomposition. Adapt the AAVB to delimit the enveloping area for objects in the whole scene. Determine the dominant axis by the vertical distribution of the listener sampling. The size distribution of boxes on the main axis in the scene are counted, and the mathematical expectation of the length is given. When solving the characteristic function, we adopt finite difference for the normal mode method to discrete the space according to the sampling point of the wavelength. Space decomposition. In pre-processing, the scene is decomposed into different computational regions. In this paper, the low-frequency domain is calculated according to different scattering regions, while the high-frequency domain is computed by an improved ray tracing method. After the pre-computed phase is completed, at the run phase we need to load the results of the pre-computed sampling point to ensure an interactive rendering rate. At runtime, prior methods either set a large number of listener locations as sampling points during the pre-computed phase, or calculate interpolation based on equal interval sampling and using distance-dependent functions. The former consumes a lot of memory space, while the latter suffers from inaccurate results. To this end, the local verification based on interpolation is used on the basis of equal interval sampling, which is helpful to realize the interactive rendering with low memory requirement. Next, we show our result. We test our method for various underwater scenes, as shown above. Table 1 shows the geometric details of our experiments. Table 2 includes the selected domain axis, the mathematical expansion L of the box size along the domain axis, boundary frequency Fd, and the number of grids Nc. Low frequency. The normal mode method takes the center frequency Fc of 1/3 octave as the sound source frequency successively, and calculates the sound pressure value of each grid point in the non-object scene. Ray tracing method is used to compute the interaction between sound wave and object, and the object scattering loss are sum of each order reflection at the source point. High frequency. The right figure provides a basis for us to set a reasonable threshold. Table 3 shows the threshold Ts1 and Ts2 per scene, and the improved retracing algorithm is compared with the sub-algorithm in terms of efficiency and accuracy. This figure shows the superposition of three scattering effects when the frequency is f equal 1165 Hz, f equal 1000 Hz, f equal 200 Hz, and f equal 20 Hz. Sound field diagram is used to represent the sound pressure loss in the scene. The color change is in direct proportion to the pressure loss. Low frequency means that the computation uses grids with less resolution and higher speed. However, it is not difficult to see that when f equals 1165 Hz, more details of the object scattering can be captured. That is consistent to that geometrical method can produce reliable sound propagation effects in high frequency domain. This paper proposed a hybrid method specific to stimulating sound propagation in underwater scenes. By integrating the normal method with an improved retracing method, the normal mode was adapted to compute the scattering of medium subdomain, while the improved retracing method was used to calculate the IR at high-frequency domain for efficiency. However, our method still has limitations. The empirical formula for boundary scattering may miss slight fluctuation of the boundary and are not suitable for random irregular boundaries. Our future work will leverage machine learning techniques to build an irregular object library to handle this issue. Since the retracing method ignores diffraction in low-frequency domain, we would include diffraction calculations in the acoustic core.